Hey guys, welcome to this video on the 2019 Level 3 Complex Number exam. So question 1, solve the equation x squared minus 4x plus 7 equals to 0. Give your solution in the form a plus or minus square root of bi, where a and b are rational numbers. Okay, so for this question, we need this is going to be complex roots, so we're going to need to use our quadratic formula. So that's negative b plus or minus square root of b squared minus 4ac divided by 2a. So in this case, negative 4 is your b value, your a value would be 1, and your c value would be 7. So we just need to plug those numbers in. So negative b would be negative 4, which is 4, plus or minus square root of 4 squared, which is 16, minus 4 times of 1 times of 7, divided by 2a, which is 2. Alright, now simplifying this, we can say 4 plus or minus square root of 16 minus 28 over 2. 16 minus 28 is negative 12. Okay, so 4 plus or minus square root of negative 12 over 2. So now we need to split the square root up. So we're going to say 4 plus or minus square root of 12 times square root of negative 1 over 2. So square root of negative 1 is just I. So 4 plus or minus I root 12 over 2. Again, this 12 can be further simplified. We can split 12 up into 4 and 3. So we can say 12 equals 4 times 3. So we can say this simplifies to 4 plus or minus I root 4 times root 3 over 2. So 4 plus or minus root 4 is 2. So 2I root 3 over 2. And this simplifies to 2 plus I root 3. So therefore, you can say that your a value is 2 and your b value would be 3. And that's just the achieved question there. So question B, when the polynomial 2x cubed minus x cubed minus 4x plus p is divided by x minus 3, the remainder is 38. So we want to find the value of p. So our remainder theorem states that if something is divided by, let's say, x minus a, that means f of a must be equal to our remainder, which in this case would be 38. That means if we have x minus 3, that's our divisor, and if we plug x equals to 3 in our polynomial, we should get 38 as our answer. So we can say that 2 times of 3 cubed minus 3 squared minus 4 times of 3 plus p equals to 38. And now we say 3 cubed is 27. 27 times 2, so 54 minus 9 minus 12 plus p equals 38. And therefore, your p value should be equal to 5. So p equals to 5. And that's another achieved mark for this question. Alright, so question C. Complex numbers u and v are u equals to q plus 2i and v equals to 1 minus 2i. Given that the modulus of u over v is 13, find all the possible values of q. Alright, so we have u over v, so we'll have q plus 2i over 1 minus 2i. That's our u over v equals to this. Alright, so right now we need to multiply by the conjugate in order to move the imaginary parts of the equation into the numerator. So we multiply by 1 plus 2i and 1 plus 2i, the conjugate. And this equals 2, so we have 1 times 1 and negative 2i times positive 2i. That should give us 5 on the denominator. And we have q plus 2qi plus 2i and 2i times 2i, 4i squared, which is negative 4. Alright, so now we're going to split this fraction into its real and imaginary parts. So real parts is just the parts without the I. So q minus 4 over 5 plus 2q plus 2 over 5i. So the modulus refers to the length on the Argand diagram. So we can say that q minus 4 over 5 squared plus 2q plus 2 over 5 squared, and take the square root of that. That's our modulus, and that should give us the 13. Alright, so now we need to simplify. So q minus 4 squared, so we get q squared minus 8q plus 16 over 5 squared, which is 25, plus 2q plus 2 squared, which is 4q squared, plus 8q plus 4 over 25. And we take the square root of this. And that should give us 13. Right, so q squared plus 4q squared, that's 5q squared. Negative 8q plus 8q, that's 0. So we can just get rid of that. So 16 plus 4 is 20 over 25 square root equals to 13. So now we can simplify this. We can say square root of 5q squared plus 20 over 5 equals to 13. And therefore, we can say that 5q squared equals to 65 squared. So that's 13 times, I move the 5 to the other side. 13 times 5 is 65. And I take the square of both sides. So 5q squared, plus 20 equals to 65 squared. So 65 squared, that's 4,225. And if I move the 20 over to the other side, it becomes minus 20. So 5q squared equals to 4205. Therefore, q squared equals to 4205 divided by 5, which is 841. And I'm running out of space here, so I just move it up here. So q therefore equals to square root of 841, which is equal to 29. However, remember, when you take a square root, you can have either the positive or negative 29, and that's equal to not p, it's q. Your q value can either be positive 29 or negative 29. That's your two answers for this question. This question I'm thinking should be in, I forgot to mention this at the start of the video. Once again, with my other 2019 videos, I don't have the marking schedule with me right now, so I cannot determine whether this is what grade a particular question is worth. However, I'm gonna give a rough estimate. So this is probably, I'd say, a merit question here. To get achieved, I'm thinking if you can rearrange up to this step here, that's enough for an achieved. Alright, let's go to question D. Question D. One solution of the equation 2z cubed minus 5z squared plus cz minus 5 equals 0. One solution is z equals to 1 minus 2i. If c is real, find the value of c and the other two equations or solutions of the equation. Alright, so we know our conjugate root theorem, which states that if sorry, I'm using red pen. So if 1 minus 2i is a root, that means its conjugate must also be a root. That's the conjugate root theorem. So if 1 minus 2i is a root, that means 1 plus 2i must also be a root. And the other root will be a real root. So in this case, we're going to say one of the roots would be 1 minus 2i, so z minus 1 minus 2i, brackets. And another root would be 1 plus 2i, which is z minus 1 plus 2i. And the last one we don't know, so we'll just say it's az plus b for now. Alright, so we can expand this out, so we can say z minus 1 plus 2i multiplied by z minus 1 minus 2i plus times our az plus b. Alright, so now we can expand the first two brackets out. We can say z squared minus z. So any parts with the imaginary parts we can just ignore, because if we multiply a complex number by its conjugate, all the imaginary parts will cancel out. So we can just ignore anything that has an imaginary part. So z times z times negative 1. So we have negative z again, plus 1. And we have plus 4 at the end. Az plus b. Alright, so now we join the like terms. So z squared minus 2z plus 5 multiplied by az plus b. So now we can expand this third bracket. So we can say az squared. Oh, sorry, az cubed. Sorry, my bad. Az cubed plus bz squared minus 2az squared minus 2bz plus 5az plus 5b, and that is our roots. Okay, so we know that one solution of the equation is 1 minus 2i. So looking at this, we know that a here must be 2, and that's because of that's the only term with z cubed. That means a must be equal to 2. So that's what we know for sure. Alright, in terms of our b value, okay, so we know if we join these two z squared values, then we'll get our negative 5. So we can say that b minus 2a equals to negative 5. However, we already determined that a is 2, so therefore b minus 4 equals to negative 5. So therefore, if we move a negative 4 to the other side, we'll have b equals to negative 1. So we found out our b value, and now we need to find c value, which is cz. So that means we can find this by joining these two together. So we have negative 2b plus 5a would be equal to our c value. We determined that a is 2 and b is negative 1. So negative 1 times negative 2, that's 2, plus 5a, 5 times of 2, so plus 10 equals to c. Therefore, c equals to 12. Alright, and it says we need to find the other two solutions of the equation. Well, we already have one of the solutions, that's 1 plus 2i. And the other solution will simply be this third bracket here. So we've determined that b is negative 1 and a is 2. So our last bracket would be 2z minus 1. Therefore, our last root would be z equals to 1/2. If I'm not mistaken. Yeah, so z equals to 1/2, and the other two roots would be 1 minus 2i and 1 plus 2i. And that would be your final answer to this question. This is definitely a merit question. It's always been a merit question in past year papers, so I'm pretty confident on this one. In terms of getting your achieved grade, I'm thinking if you can expand it to this step, or by finding the b equals to negative 1 and a equals to 2. That would be enough to get you an achieved. Alright, question E. Find the values of x and y given that x and y are real and 1 over x plus iy minus 1 over x plus I equals to 2 minus I. So in this case, you have two options. You can either do the subtraction of two fractions first, or you can find the conjugates first and then move I to the numerator first. Moving I to the numerator first might be easier. So multiplying each fraction by its conjugate and then doing the subtraction. So if we look at 1 over x plus iy, so 1 over x plus iy, and we multiply that by its conjugate, which is x minus iy, we will get x squared plus y squared over x minus iy. So this is equal to this. So now we're going to do 1 over 1 plus I. So we're going to multiply by its conjugate, which is 1 minus I, 1 minus I. And this would be equal to 2 over 1 minus I. So now that we have I in the numerator, we can now subtract the fractions. So we have x minus iy over x squared plus y squared minus 1 minus I over 2. So now we need to make a common denominator. So we can multiply the left-hand side by 2, and we can multiply the right-hand side by x squared plus y squared. So we can have 2x minus 2yi over 2x squared plus 2y squared minus 1 minus I times of x squared plus y squared over 2x squared plus y squared. So now if we expand this bracket here, so we have 2x minus 2yi minus bracket x squared plus y squared minus x squared I minus y squared I. And that's all over 2x squared plus 2y squared. Okay, so now if we expand the brackets and simplify, we'll get 2x minus x squared minus y squared. And we'll have negative 2yi plus x squared I plus y squared I. Because double negative makes a positive, remember? So then just all over 2x squared plus 2y squared. Alright, so now the next thing to do is we need to split this equation up into its real parts and imaginary parts. So we can say 2x minus x squared minus y squared over 2x squared plus 2y squared. And we're adding that onto the imaginary part, which in this case would be negative 2y plus x squared plus y squared over 2x squared plus 2y squared. Okay, so we know that this expression here would be equal to 1 minus 2i. So in this case, we know that the real part has to be equal to a real part, and the imaginary part has to be equal to the imaginary part. So in this case, the imaginary part of 1 minus 2y would be 1, and the imaginary part would be negative 2. So we need to equate both of these and solve a simultaneous equation. So 2x minus x squared minus y squared over 2x squared plus 2y squared, that equals to 1. And we know that 2y plus x squared plus y squared over 2x squared plus 2y squared, that equals to, negative 2. Alright, so now we move 2x squared plus 2y squared to the other side, so we multiply. So 2x minus x squared minus y squared equals to 2x squared plus 2y squared, and then on the right hand side it would be negative 2y plus x squared plus y squared equals to negative 4x squared minus 4y squared. So now I'm going to move everything so that everything is everything's equal to 0. So on the left hand side we'll have 2x minus 3x squared minus 3y squared, that equals to 0. And on the right hand side we would have negative 2y plus 5x squared plus 5y squared, that equals to 0. Alright, so now we need to eliminate the, we'll try to eliminate x squared and y squared. So we're going to multiply, okay, we'll say this is equation 1 and equation 2. We'll make it so the lowest common denominator of 5 and 3 is 15. So we need to multiply equation 1 by 5 and equation 2 by 3. So we have 10x minus 15x squared minus 15y squared equals to 0. And in this case, on the right hand side, we'll have negative 6y. Negative 6y plus 15x squared plus 15y squared equals to 0. So now we're going to add both of these. Equations. So we're going to add this onto negative 6y plus 15x squared plus 15y squared equals to 0. So this cancels out to be 0 and 0, and negative and 10x minus 6y, and that equals to 0. So therefore we have determined that 10x minus 6y equals to 0. Therefore, if we divide everything by 2, so we can simplify this a little bit. So 5x minus 3y equals to 0. So therefore, we can say that what should we do? We can say that 5x equals to 3y, and therefore y equals to 5x over 3. Alright, so now that we have this equation, we can now substitute this term back all the way back into our, sorry about the background noise by the way, just ignore it. So 5x over 3, we're going to substitute back into either one of these, so either equation 2 or equation 1. Let's just say I'll do equation 1. Okay, so we say 2x minus 3x squared, so minus 3y squared. But in this case, y equals to 5x over 3. So minus 3 times of 5x over 3 squared. So therefore, 2x minus 3x squared minus 3 times of 5x squared, that's 25x squared over 9. That equals to 0. So 2x minus 3x squared minus 75x squared over 9, that equals to 0. And now we can just plug this all into our calculator. Alright, so negative 3 minus 75 over 9. So therefore, we get our x value equals to 3 over 17, or x equals to 0. And, okay, so to know with this x equals to 0 solution, let's just say we use x equals to 0. That means our y also has to be 0, because we know 5x over 3 equals to y. So that means x equals to 0 and also y equals to 0. Okay, so but if you look here, if x equals to 0 and y equals to 0, then it's going to be 1 over 0. And that's impossible, so therefore that's not a valid solution. So you can say x equals to 0 gives it's irrational, like undefined, sorry, not irrational, undefined. So this is not a valid solution. So therefore your x equals to 7 over 3, that is a valid solution, because that makes the denominator something that's not 0. So therefore, if x equals to 3 over 17, then we'll find our y. So 5 times of 3 over 17 over 3 equals to y. Should give you y equals to 5 over 17. So 5 times Yeah, it gives you y value equals to 5 over 17. So that is your set of solutions. So x equals to 3 over 17 and y equals to 5 over 17. So this will be an excellence level question if you can find both of these x and y values found. To get a merit grade, okay, okay, I'm reckoning merit grade probably if you can get up to this step by splitting up the real and imaginary parts and equating them to the real and imaginary parts of the other side. That might get you a merit grade. In order to get an achieved, I'm thinking if you can just rationalize both of these fractions correctly. So what I'm saying is this correctly and this done correctly would be achieved. Alright, once again, these are just rough estimates. I don't know for sure. I'm just judging off my instinct. Alright, question 2. If p equals to 3 minus I and q equals to negative 2 plus 5i, find conjugate p minus 3q, giving your solution in the form a plus bi. So we know p equals to 3 minus I. Oh, I'm using that pen, sorry. So p equals to 3 minus I, therefore conjugate of p equals to 3 plus I. And we know q equals to negative 2 plus 5i. So therefore we can plug into a formula based, not formula, but just plug into, so 3 plus I minus 3 times of negative 2 plus 5i. So 3 plus I, negative 3 times negative 2, that's positive 6. Negative 3 times 5i, that's negative 15i. So this equals to 9 minus 14i. And this should just be an achieved level question. Just check if I did that right. Yeah, okay. Question B, 3 over 4 minus root 5 in the form a plus b root 5, where a and b are rational numbers. So basically we want to move the irrational part, which is root 5, into the numerator. So this is very similar to multiplying by the conjugate. We just want to multiply by 4 plus of root 5 in this case. So we write 3 over 4 minus root 5, and we multiply that by 4 plus of root 5 over 4 plus root 5. And this equals to, so we have 4 times 4, that's 16, plus negative 5 times negative root 5 times positive root 5, that's negative 5. So 16 minus 5, that's 11 over 12. So 4 times 3 is 12 plus 3 root 5. So therefore we can split this up to a and we can split this up into the a and b. So 12 over 11 plus 3 over 11 root 5. Therefore a equals to 12 over 11 and b equals to 3 over 11. And that would be your answer here, and that's again another achieved grade. Okay, question C. Solve the equation z to the power 4 plus 16p squared I equals 0 where p is real. So write your solution in polar form in terms of p. Alright, so in this case we want to make z the subject of the equation first. So first thing we do, we want to move 16p squared I to the other side. So z to the power 4 equals to negative p squared I. Alright, so in this question we need to apply the Modulus theorem, which means we need to convert this into polar form. So in order to do this, I think the best way to approach this question, these type of questions, is always just to draw a rough diagram. Doesn't have to look good. Okay, just any diagram that's just draw a diagram. So this is our Argand diagram, and we have negative 16p squared I. So we know p squared, okay, no matter if p is a real number, so no matter what p is, it's going to be positive. So therefore, if p is positive times negative 16, it's going to be negative something I. So you know it's going to be at the bottom here somewhere. Let's just say this is our negative 16p squared I. So in order to write it into this, the polar form, we need to find the angle, which we already know is negative pi over 2, or 90 degrees, negative 90 degrees. And our modulus will just be the length of the line, would just be negative. Well, it's not negative because the length is positive, so we say the length would be 16p squared. So in this case, we can say z4 equals to 16p squared cis of negative pi over 2. Alright, so we want to find z, so we want to find the fourth root of both sides. So z equals to so 16 to the power of 0.25, so a quarter. That gives us 2 p to the power of, so 2 over 4, which is 1/2, or we can just say square root of p, which looks better. So 2 root p cis of negative pi over 2 divided by 4, because the angle is divided by 4. So negative pi over 2, that becomes negative pi over 8. And that will be that will be our solution number 1. Alright, so we know that the power is z4, which means we know that there's going to be 4 different solutions that we can find. So the way I like to do it is, because there's 4 solutions, I'm going to split this Argand diagram into 4 sections. So each section would be, after 4 sections, I would have made 1 complete loop. So we know 1 complete loop is 2 pi, and we want to do it 4 times. Okay, so we're going to divide by 4. So we're going to add 2 pi over 4 each time in order to get our next root on our angle. That's the way I like to do it. I know some people do like the 2k, but I just like to do it like, because we have z to the power 4, that means we must have 4 solutions. So I'm gonna split this the circle into 4 different parts. We know the entire circle is 2 pi radians, which means each time I'm going to add 2 pi over 4 in order to make 1 full revolution after 4 moves. So we know z2 equals 2 root p cis of negative pi over 8 plus 2 pi over 4. So 2 pi over 4, that's 4 pi over 8. So z2 equals to 2 root p cis of negative pi over 8, so 3 pi over 8. That's our z2. And we're going to add another 2 pi over 4 to find our third root, which is 2 root p cis of 3 pi over 8 plus 4 pi over 8. And that would give us z3 equals 2 root p cis of 7 pi over 8. And to get our final root z4 is equal to 2 root p cis of 7 pi over 8 plus 4 pi over 8, which is 11 pi over 8. And that should be your 4 roots. I think a good way to check your answer is to add another 2 pi over 4 to see if you get back to your original answer. If you do, that means you didn't do anything wrong. But if you don't get to back to your z1, that means you might have done something wrong. So z4 equals to 2 root p. So I'm going to add another 2 pi over 4. So becomes 15 pi over 8. And this is negative pi over 8, which means it's from the other side. So if we do 15 pi over 8 minus 2 pi, we should get back to negative pi over 8, just to check. So 15 pi over 8 minus 2 pi over 1. So therefore 15 pi over 8 minus 16 pi over 1. And that does, not 1, 8. And that does give us negative pi over 8. So that means I know that I've done the question correctly. So just as this is just like a final, to check your answer, you just add another 2 pi over 4, and that's just to double check that you get back to your first root, that you've made 1 complete circle, and that you didn't make any numeric mistakes along the way. Oh, sorry, I rubbed out the wrong thing. Okay, so finding all 4 roots in this case, that should be a merit grade, and to get an achieved grade, if you can just convert it into a polar form and maybe find one root perhaps might get you an achieved. Alright, question D. Find all the possible values of m that makes z equals to root 3 plus mi over 1 plus root 3i, a purely real number. So a purely real number, that means the imaginary part of z must be equal to 0. So there's no imaginary part, therefore it's purely real. So once again, we have I on the denominator. We want to move it to a numerator. That's the first thing we do. We're going to multiply by the conjugate. So root 3 plus mi over 1 plus root 3i. We're going to multiply that by 1 minus root 3i over 1 minus root 3i. This equals to 1 times 1. That's 1, and then that should be so negative root 3 times positive root 3, that's negative 3. Negative 3i squared, which is positive 3. So 1 plus 3 is 4 on the bottom. And need to expand it out here. So root 3 minus 3i plus mi negative root 3 plus root 3m. Okay, so we know that our imaginary part must be equal to 0. So first thing we want to do is we want to split this fraction into its real parts and imaginary parts. So real parts would be root 3 plus root 3m over 4. And the imaginary part would be negative 3 plus m over 4 times of I. So we know that this whole fraction must be equal to 0 because our imaginary part of z has to be 0 in order for it to be a purely real number. So we know that negative 3 plus m over 4 equals to 0. Therefore, negative 3 plus m equals to 0. Therefore, m should be 3. Yeah, I don't know why it says find all the possible values. I'm only getting just m equals to 3. Yeah, I'm not too sure, but... yeah, it says find all the possible values, which makes me think that there's more than one, but the math tells me that there's only one, so I'm just gonna stick with it for now. If you think I've made a mistake, don't hesitate to put it down in the comments below. But that's what I'm getting right now. And in terms of this, because this should be a merit level question, because usually that's how they do it. Like they do 2 achieved questions, then they do 2 merit questions, and then finishing with an excellence question. So this should be a merit level question, and achieved possibly if you can just split it up into its imaginary parts and then real parts, that might get you an achieved. Alright, moving on. So we have question E. If the modulus of z equals to 1 and z is not 1, prove that 1 plus z over 1 minus z is purely imaginary. Okay, so first thing, let's make z equal to a plus bi. So that's our complex number. We know that modulus of z equals to 1. And that means square root of a squared plus b squared must also be equal to 1. And if we square both sides, we'll get a squared plus b squared is equal to 1. We'll just leave this on the side for now because it will be very useful later. So 1 plus z is 1 plus a plus bi. And we divide it by 1 minus a minus bi because it's 1 minus z, so 1 minus everything. So 1 minus, sorry. So that becomes 1 minus a minus bi. Okay, so we want to move the i's to the numerator, so we're going to multiply by the conjugate, which is 1 minus a plus bi. So we just, conjugate is just flipping the sign of all the imaginary parts. So 1 minus a plus bi. Got a little bit of expanding to do. Once again, for the denominator, you can ignore anything that has an I in it, because you know when you multiply something by its conjugate, then anything with any imaginary part will just cancel each other out, so you just don't have to worry about that. However, for the numerator, because you're not necessarily multiplying by the conjugate, then you're going to need to write everything out, okay? But for the denominator, because you know that you're multiplying the denominator by the conjugate, then you just ignore anything that has an I in it. So for example, if we have negative bi times 1, you can just forget about it because we know there has to be a positive bi to cancel that out. So 1 minus a minus bi times 1 minus a plus bi. So we're going to have 1 minus a and minus a again, plus a squared, plus a squared plus b. No. Yeah, just trying to make sure I don't make any mistakes here. So a minus bi plus b squared. That's at the bottom. However, we know a squared plus b squared is 1, so that's going to be equal to 1. So we can just get rid of this and we can just say plus 1 actually. Okay, so for the top, we'll have 1 minus a plus bi. So plus bi plus a minus a squared plus abi plus bi minus abi. And bi times bi, that's negative b squared. Okay, so now we can simplify this a little bit more. So say this equals to, okay, so positive abi and negative abi cancel out. We'll have negative a and positive a cancels out. And we have, so we have negative a squared minus b squared plus 1. So I'm just crossing out, so a minus b, we have 1, and then plus 2bi over 1 minus 2a, no, 2 minus 2a, sorry. Alright, so that's what we have. So we have negative a squared minus b squared minus 1 plus 2bi over negative 2 minus 2a. So we're going to split this up into its imaginary part and real part. So we're going to say negative a squared minus b squared plus 1 over 2 minus 2a plus of 2b over 2 minus 2ai. So we want to prove that this is purely imaginary. That means that the real part of z equals to 0. So how are we going to do that? So we have a squared plus b squared that has to be equal to 1. We have negative a squared and negative b squared. So notice that we can multiply everything in this equation by negative 1. So if we do that, we'll have negative a squared minus b, not a, what am I doing? Negative a squared minus b squared equals to negative 1. So we can plug this in, plug negative 1 in instead of negative a squared minus b squared. So what we'll have is negative 1 plus 1 over 2 minus 2a plus 2b over 2 minus 2a. And this actually simplifies, the numerator simplifies to 0. So therefore, you can say that the real part of z equals to 0. Hence, this is hence 1 plus z over 1 minus z is purely imaginary. And that should be an excellence level question. So if you can justify up to here, you should be able to get an excellence mark for this question. In terms of getting a merit mark might be merit part. Merit part might be able to, if you write it up to here with the a plus a squared with this equation, you might get a merit grade. And if you can just have either one of these equations, so you can either have a squared plus b squared equals to 1, or you can have this bottom equation that can either one might get you an achieved. Alright, question 3 now. Question 3, if u equals to q squared, cis of 3 pi over 4, and v equals to q cubed, okay, that's a mouthful. So v equals to q cubed, cis pi over 3, write u over v in the form of, in polar form. Alright, so we know that u over v is q squared cis of 3 pi over 4 over q cubed cis of pi over 3. And that equals to u over v. So we know that when we divide two complex numbers in polar form, then we're going to have to, so the modulus will divide while the angle will subtract. So q squared over q cubed, that's going to give us 1 over q, cis of 3 pi over 4, 3 pi over 4 minus pi over 3. So 1 over q cis of, we'll simplify this, so 9 pi over 12 minus 4 pi over 12. Therefore, 1 over q cis of 5 pi over 12. And that's done. That's all we had to do. It didn't tell us to convert to rectangular form or anything, so that's your final answer, and that will get you an achieved. Okay, question B. If x and y are real numbers, and x plus iy times of 2 plus I equals to 3 minus I, find the values of x and y. Alright, so first things first, we're gonna expand the brackets. So x plus iy and 2 plus I, we know that equals to 3 minus I. Therefore, 2x plus xi plus 2yi minus y equals to 3 minus I. So now we're going to equate our real parts to a real part and the imaginary parts to be imaginary parts. So we're going to say that 2x minus y equals to a real part, which is 3 in this case. 2x minus y equals to 3. And we have x plus 2y equals to negative 1. Negative I just means it's negative 1i, so it equals to negative 1. Okay, so for this, I'm going to solve simultaneous equations. So once again, I'll say this is equation 1, equation 2. Let's just eliminate variable x. So we're going to say 2 times of equation 2, so 2x plus 4y equals to negative 2. And we're going to subtract, subtracting equation 1, we'll get subtract 2x minus y equals to 3. 2x minus 2x is 0. 4y minus y, that's 5y, equals to -2 minus 3, which is equal to -5. So therefore y equals to -1, and x would therefore be equal to, so we just plug it back into this equation, for example. So let's say x minus 2 equals to -1. Therefore x equals to 1. So just let me double check this with my calculator real quick. So it should be correct. So 2, 3, and 1, 2. Yeah, this should give us a 1 and -1. That should be. So this should be your final answer for this question, and that's again should be another achieve mark here. So question C, solve the following equation for x in terms of w. So we have 2 root, red pen again, sorry, I keep forgetting. Okay, so 2 root x minus 3 equals to w root x. So we want to separate the square roots. The reason we want to separate these two square roots is because if we just like, for example, if we just square this right away, then we're going to get another square root's going to come out, and that's just going to be a real handful. Like another, like there's going to be more square roots that you have to cancel. But this way, you can make it clear, square root 1 on the other side and another square root on the other side, so it becomes, makes it easier for us. So if we square both sides, so we say that 4 times of x minus 3 equals to w squared times of x. So therefore 4x minus 12 equals to w squared times of x. So what do we want? We want to solve the following equation for x in terms of w. So x equals to something w. Alright, so what should we do here? So -12, we can move 4x to the other side. So we can say -12 equals to w squared times of x minus 4x. And on the right hand side, we have grouped the x's together. So now we can take x as a common factor. We can take x as a common factor. So -12 equals to x times of w squared minus 4. And therefore, -12 over w squared minus 4 equals to x. And that should be your final answer here. So double check. So yeah, that should be your final answer, which is a merit level question. To get an achieved, if you can possibly getting up to this stage, actually might be enough for an achieved. I'm not too sure though, but just gut instinct. Let me just check if I done this right. X. Yeah. Okay. Sweet. Question D. Two complex numbers are defined by u equals to 1 plus pi and v equals to 5 plus 3i. Given that the argument of u over v is pi over 4, find the value of p. So first thing, we're going to write out our u over v. So our 1... Oh my gosh. Okay, so we have our 1 plus pi over 5 plus 3i. That's equal to our u over v. And we know that argument of u over v is pi over 4. But first we want to... Okay, let's not jump into that too quickly. First, we want to move all the imaginary parts to the numerator. So we're going to multiply by the conjugate, which is 5 minus 3i. 5 minus 3i, which is equal to... So you have 25 and 25 times... Okay, that's 25 plus 9. 25 plus 9 is 34. And on the top, we'll have 5 minus 3i plus 5pi and negative 3i times pi, positive 3p. Okay, so now we want to split this into our real and imaginary parts. So 5 plus 3p over 34 plus negative 3 plus 5p over 34 times I. Okay, so for this case, so now we want to, once again, anything that they give you with arguments, I strongly suggest that you draw a rough sketch of a diagram. So in this case, we have our argument of u over v is pi over 4. So we know that pi over 4 is in the first segment. Okay, it should be somewhere. Let's just say somewhere there. So this angle we know is pi over 4. This would be our y, and this would be our x. As in, our y is our imaginary part, and the x is our real part. So if we write tan, sorry, what am I doing? I'm getting too far ahead. So if it's a right angle triangle, so we can use trig rules. So we can actually say that tan of pi over 4 equals to y over x. So therefore, if you plug in tan pi over 4, the thing you should notice that tan pi over 4 equals to 1, which is really handy for us actually, because we can now say that x equals to y, because the left hand side is 1, so therefore x equals to y. So therefore, we can just say that 5 plus 3p over 34 equals to negative 3 plus 5p over 34. Okay, they have the same denominator, so you can just ignore them, and you can just equate the numerator, so even more handy. So 5 plus 3p equals to negative 3 plus 5p. Alright, so if we move negative 3 to the other side, so we have 8 equals to 5p minus 3p, which is 2p. Therefore, we have our p equals to 4. And that should be your final answer for this question. And this should be a merit level question with an achieved perhaps up to this stage. So writing it in the real parts and the imaginary parts, that might be an achieved. Okay, question E. Prove that the quadratic equation x squared plus 3kx plus k squared equals to 7x plus 3k will have two distinct real roots for all real values of x, not x, k. So for this question, we want to prove that the discriminant is always greater than 0. Because if we prove the discriminant is always greater than 0, then we'll know that there's always two real roots. So we want to make, in this case, this is a quadratic, we want to make everything equal to 0. So first things first, we have x squared plus 3kx plus k squared minus 7x minus 3k that equals to 0. So now we're going to do a little bit of factorizing so we can make our a, b, and c values a lot more clear to us. So we can say x squared plus 3k minus 7 of x, because this x and this x is the same, therefore we can group the 3x and the negative 7. And we say plus k squared minus 3k. Okay, just a note, this k squared is a constant, therefore it's going to be the c value. I've seen some people before, they did 1 plus k x squared, but k is not x in this situation, so you cannot actually group them together. K is actually just a constant that we don't know, which means that it's a c value, not the a value. So we know that our a is 1, b is 3x minus 7, and our c is k squared minus 3k. So therefore, we can say that quadratic formula, once again, negative b plus or minus b squared minus 4ac over 2a. Alright, so we have negative 3x plus 7 plus or minus square root of 3x minus 7 squared minus 4 times of k squared minus 3k. Okay. Sorry, I forgot to divide by 2. Okay. Negative 3x plus 7 plus or minus square root of 9x squared minus 42x plus 49 minus 4k squared plus 12k over 2. So we have negative 3x plus 7 plus or minus square root of 5x squared minus 30x plus 49 over 2. And this here is our discriminant. So what we want to do, okay, so we could have just found our discriminant. We didn't have to do all the quadratic formula, but too late now. But we could have just found the discriminant. So we want to prove that this is always greater than 0. And that's how we can have always have two real roots, okay? So actually, for this question, I decided so we can just say 5x squared minus 30x plus 49. Okay, so first things first, we want to prove that this is always not touching the x-axis, because if it's touching the x-axis, then it's going to be equal to 0, and therefore there could be one solution, and that's not what we want. So we're going to find the discriminant of the discriminant. So discriminant of 5x squared minus 30x plus 49. So we're going to use quadratic formula again. So we're going to say, but this time we're just going to find the discriminant. So b squared minus 4ac. So this time 900 minus 5 times of 4 times of 49. What does that give us? 5 times of 4 times of 49. That gives us 980, which means that this expression equals to negative 80. Okay, so this is less than 0, which means that for this discriminant, that it never touches the x-axis, which is good news. However, there's one problem. The one problem is that we do not know if this discriminant is always below the x-axis or always above the x-axis. Because if it's always below the x-axis, then there will always be no real roots. However, if it's always above the x-axis, then we can prove that there are always two real roots. So one thing to note down is that the shape of this parabola is a positive parabola, which means it has a shape like this. I'm not saying this is the graph, I'm just saying this is the shape of the parabola, which means it's going to have a vertex, okay, a vertex that is somewhere. We want to prove that this vertex is always above the x-axis. If we can prove that the vertex is above the x-axis, which is the lowest point, then we can prove that the whole parabola is above the x-axis, and hence there will always be two real roots. So if we take our expression, which is 5x squared minus 30x plus 49, if we make that our f of x, then we can actually differentiate this, and then we can find our turning point, which is our vertex in this case. So if we say f dash of x equals to 10x minus 30, and we can make this equal to 0 in order to find our turning point. So 0 equals to 10x minus 30. In this case, our x is equal to 10. And why did I put 10? Why did I put x? Isn't it k? It's k, isn't it? Oh my god, what am I doing? Oh, okay, guys, apologize. It's supposed to be k, just not x. It's k. I forgot about it. Sorry, guys. I apologize once again. It's supposed to be k. Apologies for that once again. Doing this in terms of k. So k equals to 3. So now if we substitute 3 back into our equation, then we say 5. Okay, so we know that this is our vertex point because it's at our minimum, and there's only one turning point in the parabola. So we know this is a positive shaped parabola, which means our turning point must be our minimum. So that's our minimum point of the parabola. So the parabola can't get any lower than this point. Therefore, if we prove that this lowest point is above the x-axis, then therefore the whole parabola has to be above the x-axis, and therefore this expression is always greater than 0, and hence there will always be two real roots for that particular equation. So if we say f of 3 equals to 3 squared minus 30 times of 3 plus 49. Okay, so 3 squared times 5 minus 90 plus 49. That gives us a equals to 4. That means the lowest point of this parabola is equal to 4, and therefore, because 4 is greater than 0, we can say that we can say something like this. Because the minimum point, or we can say this is vertex of the parabola is greater than 0. We can say is greater than 0. Hence we can say the parabola is always greater than 0. Hence the discriminant, so the discriminant will always be greater than 0. And always greater than 0, hence two real solutions. So just write something like that, just a justification for your answer. That should get you up to the excellence mark. To get a merit mark, if you can find okay, perhaps if you go up to here and you don't justify whether the parabola is above or below the x-axis, you might get up to a merit grade for this. And to get an achieved grade, if you can be able to, oh, it's a tough one. I'm not too sure actually. If you can, perhaps if you can find the discriminant, but maybe if you can just find the discriminant, you might get an achieve. But I'm not too sure on that one. Right, so for this question, I was trying to think of an algebraic way I could do this, but it didn't really come to mind, I guess. But so if you had a better way that you could use algebra to find the answer to this question, I would love to hear about it in the comments below. Anyway, other than that, thanks for watching this video, and I hope you all enjoyed, and I hope to see you all in the next one.